complicated is the function using the rules of differentiation, chain rule, product rule, quotient rule, and so on. You can compute the derivative without problem. Now, in our course, the major problem will be the following. You know the derivative of the function, and you need to reconstruct the function itself. In other words, find the function whose derivative is given to, is known, like in this example. So let's assume that you know that the derivative of some function is x squared. So how does the function look like? And if you recall the table of derivatives, and after some thinking, you probably can come up to the solution, right? If you take the function x cubed divided by 3, and if you differentiate it using usual rules of differentiation, constants is taken out, the derivative of x cubed is 3x squared, so 3 is canceled out, and you get x squared. Okay? So at least this simple calculation shows that this function x cubed divided by 3 is one of the possible functions such that its derivative is equal to x squared. But instead of having a function x cubed divided by 3, I can choose, for example, x cubed divided by 3 plus 10. Right? And if you differentiate using addition rule, the derivative of this term is 0, and the derivative of the first term is x squared. So we can say that the derivative of this function is also x squared. So if I choose another constant here, instead of 10, say minus 3, the result will be the same. And I can even choose an arbitrary constant c. So taking into account that the derivative of c is 0, this is what you get. So this is our first conclusion, that if you know the derivative of the function, you cannot uniquely reconstruct it. So there is always this arbitrary constant that needs to be added, okay? And therefore, we use this term antiderivative of f. This is a capital F, for example. This is a problem that we need to solve. Once again, small f is known. How do you find capital F? How do you find the function whose derivative is equal to small f? Okay. And this function is called antiderivative of f. So that, in fact, this simple analysis with our example of the function x squared shows that there are infinitely many antiderivatives for the given function, and all these functions are different apart from arbitrary constant. Okay, we have another question. Well, as I said, I made a record on the previous classes, so I do not think that this is worth thing to do. So all the videos will be available. So let us do it like a live session, and you can also ask questions. So I will not record my lectures. They are already recorded previously. Okay, so what we found is that there is not a single antiderivative, but infinitely many. And there is a special notation in calculus to denote the set of all antiderivatives of the given function. So this symbol is the following. So it's a kind of this is the whole notation that we'll be using quite often this semester. So first of all, this symbol, it looks like a stretched letter S. It's called the integration symbol. So this function is the integrand. And we also use this notation dx. This is differential of x. At the moment, this notation does not seem to be logical and clear. So why should we use so complicated notation to denote antiderivative of the given function? But at a later stage, when we start to compute definite integrals, then this becomes clear that really a definite integration is some sort of a limited form of addition. Okay, so that's why this symbol Makes sense. So the procedure of finding all antiderivatives of the given function is called integration. Okay? So we say that, like in our previous example, right? If I use a new language, we know the derivative of the function, and then we can say that the integral of the function x squared is this expression in parentheses, right? So this is a terminology. Now, how do you interpret this fact geometrically? Well, if you have a function, say y equals f of x, then geometrically it represents some curve, which is shown here with the red color, some curve in the xy plane. But then if you add or subtract arbitrary constant, then you obtain another graph which is actually shifted parallel to the red curve, either upwards or downwards, right? For example, if you have C1 some positive constant like 1, this means that this curve should be lifted by 1 unit. So we can say that we transform this curve parallel to itself by 1 unit. If C2 is equal to 10, for example, then you need to lift or move this red curve by 10 units in the positive y direction. If C is negative, then you similarly transform your red curve to the blue ones. For example, C3 may be equal to -2 and C4 may be equal to -4, for example. So in fact, the set of all antiderivatives of the given function is represented by a family of functions, family of curves in the xy plane for different values of the constant c. So once again, terminology, and this is what we will use. This notation will be used quite often. So once again, the small f is the function, is the derivative of the given function. And we want to reconstruct the function if the derivative is known. So this symbol is integral sign. This function is called integrand. X is a variable of integration. So this whole thing is called the indefinite integral. And c, in this case, should be added all the time. So it is a constant of integration. Now, let us look at some important properties of indefinite integrals. So first of all, these operations, integration and differentiation, they are kind of inverses of each other. So if you differentiate the integral, you will get the integrand. And the way to prove it is very simple. So we assume that capital F prime is equal to small f. And if I differentiate the integral, this means that I differentiate this expression, and the derivative of the expression in parentheses is f prime, capital F prime of x. But capital F prime is small f. So this is one thing. And by the way, this is how we can check whether the calculation is correct. So let's assume that we calculate this integral and found the following answer. Now, in order to prove that this is a correct answer, you can differentiate the right-hand side. And if the derivative of the right-hand side is equal to the integrand, then this operation is correct. So you can check using the rules of differentiation that the derivative of this function is equal to x squared plus 5x. So this is the integrand. Therefore, calculation is correct. Of course, we are not going to do it all the time. So, but in some cases, if you have doubts that integral is correctly calculated, just differentiate the right-hand side and see whether the derivative will be equal to the integrand. Now, similar property 2 formulated for differentials. So if you take a differential of the integral, then it is equal to this product, f times dx. And again, the proof can be found using, first of all, the definition of differential. if y is a differentiable function, then differential of y is equal to y prime times dx. And if you do that, we can show that this is the result, okay? The other properties are more useful, let's say, in practice. When you perform actual computations of integrals, then it's good to know that if you just integrate differential of some function, then the result is this function, okay, plus c. And again, the proof is found using the definition of integral and the relationship between the derivative and the differential. So property number 4 tells us, and I strongly recommend you to use it, whenever you have a constant factor under the integral sign, you can take it out. So it can be taken out, and then just integrate f. So again, this is a simple proof. Now, property number 5, we also use it quite often in practice. If you need to integrate algebraic sum of 2 or more functions, then you can integrate each function separately and then either add or subtract them. Okay? So these properties number 4 and 5 are always used and almost in any integration example. So what is very important in a theory of indefinite integrals is this property number 6, which is known as invariance of integration formulas. So how do you understand this? That integration formula remains its form even if the argument is not an independent variable, but some differentiable function of x. So in other words, if I know that the integral, for example, of f of x is equal to capital F of x plus c, then similar expression holds for this case, assuming that now arguments x here and there is replaced by some differentiable function of x. To illustrate, let's look at this example. So we already know that this integral of x squared is x cubed divided by 3, right? Now, let's assume that, and what this formula tells us, that if I replace x with u here and there, then the right-hand side also will contain the same expression where x is replaced by u. Okay. So in particular, if instead of x here, I would have cosine x, that is integral of cosine squared times differential of cosine squared is cosine cubed divided by 3, right? Similarly, if I replace x here and there by logarithm, then integral of logarithm square, assuming that logarithm is also on the differential sign, is logarithm cubed divided by 3. This is how it works. But if I have integral, say, of cosine square x dx, if I do not have this cosine here, then the answer will not be cosine cubed divided by 3. So we shall work with this property later today and during a tutorial session. But this is very important. It allows us to compute integrals or extend the class of integrals that can be evaluated in closed form. So next step, here is the table of integrals. This is not complete. This is just an example of some of the integrals that will be used in practice. And I also would like to show you, again, you do not see it at the moment, but when everything will be fixed, you will see also this link or this header tables and formulas. And for each group, we have a list of formulas. I think they are quite well designed. And for example, this is how the table of integrals look like. For your convenience, we show here basic properties of integrals, then basic formulas, and also in the last column, a table of derivatives. So you see that all the formulas for integration and differentiation are written in terms of u, assuming that u is a function of x. So sometimes it's also helpful. That's why the table is there. And it is a two-page table. So this is the second page. And it shows the different integration methods that will be discussed later: integration by parts, integration of rational, trigonometric functions, and so on. So my strong advice is to have it with you all the time when we look at when we solve problems, and it will be a very good idea if you print it out and have it. I understand that everyone now is using mobile, but if we switch to the normal mode, all the exams and tests will be closed book. So we only allow you to use this table. So that's why it would be great if you can print it out and have it with you starting from the next class. Okay. So how do we derive all these formulas? Well, in fact, you need to recall differentiation rules. For example, y integral of a cosine is sine. Since the derivative of this term, if you differentiate the right-hand side, you get cosine, right? So that's why the formula is correct. Remember again that if you differentiate the right-hand side, you should get the integral. Y integral of sine is minus cosine because the derivative of this function is sine of x with a plus sign, and so on. The derivative of tangent is 1 over cosine squared. The derivative of cotangent is minus 1 over sine squared. That's why if you put a minus sign here, you have a plus sign here. We do not ask you to memorize this formulas, but it will be a good idea if you still have it all the time with you, because integration process is much more complicated than a differentiation procedure, because each integral, if you want, requires individual approach, right? And therefore, the knowledge of this table and the understanding what kind of a typical integral that you can use should be very helpful. Well, this simple cartoon show what is the meaning of a differentiation and integration. So this is milk. So if you differentiate it, you get cheese, right? Processed milk. But if you integrate, you get this object that you can see on the right-hand side. All right, so this is again very, very important. So that's why integration is more complicated, because we cannot formulate universal integration rule. As we mentioned before, you can always differentiate function no matter how complicated is it. So if you know chain rule, product rule, quotient rule, table of derivatives, you can do it. For integration, this is not the case, and there are even situations, and there are many of them, when you can't provide the answer in closed form. So that's why this process is more complicated. Now, I would like to illustrate this with a few examples, and during the class, I'm using the Blackboard on Zoom. So let us start with the first exercise. So we need to evaluate this integral. So another question here. Well, this is called whiteboard. Yeah, whiteboard on Zoom. So we have a graphical tablets that allow us to write formulas on the board, and for calculus courses and math courses, this is extremely useful thing. So what does this notation mean? We would like to find a function whose derivative is equal to the following expression, okay? And this is a time when we need to look at the table of derivatives. So if we look at the table of derivatives, for your convenience, I would show you one particular example. So this integral, if you integrate x to the power alpha, is x to the power alpha plus 1 divided by alpha plus 1 plus c if alpha is not equal to minus 1. So this is the only exception where this formula does not work, because you will have a 0 in the denominator. So the idea is then to transform this integral to this form, right, using properties of the integral. I will do it in detail. So first of all, let us divide these two quantities. 2x to the power 7 divided by 2x to the power 5 is 2x squared, right? Plus 3. Now this expression, this is x cubed. Maybe it is not so clearly written. So whenever you have roots, you need to transform it to powers, so that square root of x cubed is x to the power 3/2 divided by x to the power 5 minus 5. And then what we do next, we rewrite this integral as algebraic sum of three integrals. One is of 2x squared, then the second one is 3. And now we use the properties of exponents. So recall that if you have x to the power m divided by x to the power n, this is equal to x to the power m minus n, right? So in this case, m is 3/2. Sorry, again, missed x. So x to the power 3/2 minus 5, right? And the minus integral of 5 times dx, okay? So let's continue here. Remember that constant can always be taken out. So this constant also can be written in front of the integral. And this becomes, let's perform this computation here. This becomes x to the power minus 7/2, right? And in this case, the constant 5 can also be taken out. So now let us look at this main formula that will be used now. So for this case, alpha is equal to 2. So that the answer is 2 times x to the power 3 divided by 3 plus 3. In this case, again, alpha is minus 7/2. So we have x to the power minus 7/2 plus 1 divided by minus 7/2 plus 1. And in this case, we have a 1, a constant 1, so which corresponds to alpha equals 0, right? So if alpha is equal to 0, then we have x. You can also use one of the properties of, remember, of the integral, that if you integrate the differential of some function f, then the result is f plus c. And then we add an arbitrary constant. So please note that strictly speaking, I need to add the 3 arbitrary constants, for example, C1 here, C2 there, and C3. I can do that, of course, but the sum of 3 arbitrary constants, which could have added, is still an arbitrary constant. So it's sufficient just to have one of it. And this is our final result, 2/3 x cubed minus, so we have what, 6 divided by 5, x to the power minus 5/2 plus, minus 5x plus c. Okay. Let me now answer your questions. Okay, x to the power 7. Yes, we have x to the power 7, but then we divide the 2. So we use this property 7 minus 5 is 2. So we have x squared. So I didn't differentiate anything. So we are computing integrals. There is no derivative here, right? So what else? Yeah, divided by x to the power, well, it should be exponent, right? You see this rule here? X to the power 7 divided by x to the power 5 is x to the power 7 minus 5. Okay. So what else? All right. So with a little bit of experience, most likely you would omit all these steps. And after that, when you have this, you can write down the answer. Right? But initially, when you're just practicing with integration, my advice is to do it in detail so that you will understand these basic rules better. All right, let us solve a problem 2. I'll try to do it here. Well, the first thing you need to do whenever you have integral, just look at the table of integrals, okay? So you open this table and see whether there is an example that you can use immediately among the functions in the second column. So if you can't find one, then think of some sort of a transformation. And in this case, the transformation is to divide by x each term. So I can rewrite it as a sum of 2 integrals. Again, I will do it in detail just to simplify things. So here constant is taken out, so it's 7. Then integral dx divided by x plus 3 is also taken out, and we have x to the power 3 here. Okay. Now, this integral is in the table, and it is natural logarithm, so that because the derivative of the logarithm is 1 over x. This is from the same category that we see here with alpha equals 3. So 3 x to the power 4 divided by 4. So this is the final result. Do not forget to add this arbitrary constant. As I mentioned before, you could have added 2 arbitrary constants, but the sum of 2 arbitrary constant is another arbitrary constant, so that we usually add this constant after all integrals are evaluated and add it just once. Okay. And the third example from the list that is shown in the notes is the following. So, if you open your table of integrals, you will not find such an integral in the table. Let's open the parentheses. So multiply this expression in parentheses by e to the power x. So we have e to the power x minus e to the power x times e to the power minus x cosine x. And if you do some other simple manipulation, because this product is actually equal to e to the power 0. Remember again the properties of exponents. If you multiply x to the power a and x to the power b, if the base is the same, this is x to the power a plus b, right? So I need to add these two quantities, which gives me 0. And since e to the power 0 is 1, so that we obtain a rather simple expression. And let us again split this integral into two. We always use, in many cases, algebraic sum, this property of integrals. And then you open your table of derivatives. So if you do it, well, one inconvenience in using this board is that in order to show you something else, I need to stop share and share it again. Unfortunately, there is no other option unless you use some specific software, but this is still much better than without the tablet. So this is one integral from the table, so that I can just write down e to the power x. As I said, arbitrary constant will be added later. And we integrate cosine. Then from the table, you observe that we get sine. Okay, so this integral is minus sine. And then I just add an arbitrary constant. And this is a result. Again, you can verify differentiating this expression that you get this. The derivative of this function is e to the power x minus cosine x. So these are some very simple examples and exercises, and we can use this invariance property of integrals to perform calculations for more complicated cases. And the way we usually describe it is the following. I didn't find such an approach in English-speaking literature, but this is what we do here. We call it the transformation of a differential. So in other words, let's assume that I need to integrate this function, okay? Integrate sine of x minus 3. So we know from invariance property that this can be done. You can use table if you would also have x minus 3 on the differential side, right? And in order to achieve that, we can just add arbitrary constant here, okay? So we know this formula, that the differential of any function is its derivative times dx, okay? If I need to compute, let's assume that u is x plus c, okay? Then the differential of x plus c is equal to the derivative of this term, which is equal to 1 multiplied by dx. So what this formula shows that differential of x can be easily replaced by differential of x plus c. So if needed, you can always add arbitrary constant on the differential side. And this is the approach that can be used to evaluate all these integrals. But let me first answer your questions. All right, so I do not see any question. In fact, okay. So how do we perform this calculation? Again, I'm switching back to the whiteboard. So let's call this example 4. So we need to integrate sine of x minus 3 times dx. So we have this formula in the table. Integral of sine u du is equal to minus cosine u plus c, okay? But you can always use this formula if you have the same expression under the function and under differential sign. Here we have x minus 3, but in this case just x. But as we discussed already, dx can be easily replaced by by such a differential where c is any constant. In other words, in order to integrate, I can just add this arbitrary constant minus 3 on the differential sign, right? So this is because of this, right? And now we have the same expression, okay? U here and there. So therefore, I can use this formula where u will be replaced by x minus 3. So the answer is minus cosine of x minus 3 plus c, okay? So that you can always add arbitrary constant, positive, negative, does not matter. So another example in the formula sheet is on the presentation is the following. So again, in the table, if you look carefully, you will see such a formula. Okay, but again, it can be used if and only if these expressions are the same. So they are not the same here, but I can make it like this. So I can simply replace dx. I want to have x plus 4 on the differential sign, and this can easily be achieved. So now we can use invariance of integration formulas where the role of u plays this expression x plus 4. So the answer is tangent of x plus 4. And one more example. So the first thing, we look at the table of integrals. You will see integral of this form. And it is equal to arc sine of u divided by a. Okay. So in this case, this first term is a squared. So a is equal to 5. And but these expressions are different, right? So if I would have x minus 4 on the differential sign, then I can use this formula. But this can easily be achieved because of this property here. So I can rewrite the numerator as the differential of x minus 4. And then this expression can be written as 5 squared minus x minus 4 squared. And now if you compare this integral with the one in the table, you see that if u is equal to x minus 4 and a is equal to 5, then we can write the answer. So the answer is arc sine of x minus 4 divided by 5. So this is the whole argument under arcsine function. Any questions, comments here? Okay, let me switch back to the presentation. So this is the first kind of a simple transformation. If needed, you can always add arbitrary constant on the differential sign. Now, what about the factor? If I need to have a factor on the differential sign, then I can multiply and divide by c. So in other words, dx can be written like this, and you can verify it. How do we compute the differential of cx? So this is a definition of a differential, derivative times dx, and the derivative of this term is capital C. So in other words, if I solve this equation for dx, then we get the following result. In other words, if I need a constant factor under a differential sign, then I need to multiply and divide by this constant. so that the result will be correct. Okay. Now let's also kind of learn a little bit more this table of integrals. So how do you compute this expression? Integral of 3 to the power 2x. Let me show you the table of integrals. And here is the formula, right, that you can use, okay? So I can use this formula if these expressions are equal. We have a to the power u times du, right? But in my example, we have 3 to the power 2x, but I do not have 2x on the differential sign. So I have to have it. And the way to do it is to multiply and divide by 2. So let me continue with the whiteboard. So this example 7, I guess. Again, as a reference, you can use this formula from the table. But it is valid if and only if these arguments are equal. They are not. So I cannot modify this argument, but I can do something with this. So in other words, what I can do next, I can multiply by 2 and divide by 2, right? So as we show that this, the result will be the same. Now I can take this constant out, 1/2. And now you see that I can integrate this result, right? So if this is u, these expressions are equal. So I can write the answer where u is replaced by 2x and a is equal to 3. So 1/2 and 3 to the power 2x divided by logarithm of 3 plus c. Well, this is another way of evaluating integrals. Let's practice a little bit more. So, reference to the table of integrals. I will not do it all the time, just the first class. The rest, it's your responsibility to have it in front of you. So without the table, as you can see, we cannot go further. So please make sure that you have this table next time with you. So this is a formula from the table of integrals. The difference is that now we have x divided by 3, but x here. So what I would like to do is to have, say, x divided by 3 here. Then it should be okay. And I can integrate. But what I need to do is to multiply the result by 3. In other words, I divided by 3 the argument to make sure that these arguments are the same, but I need to multiply by 3 to make sure that these expressions are equal. And then we integrate. So this is minus 3 times cotangent of x divided by 3 plus c. So one more exercise, integrate cosine 5x. Again, in the table, you have integral of a cosine u, which is equal to sine u plus c. But again, this formula can be used if and only if these arguments are the same. In our case, we do not have the same argument. So we don't have this factor 5, but we multiply and divide by 5, and this is the solution. Okay, and then this constant 1/5 can be written in front of the integral. So now everything is clear. So we have the same expression here and there, so that the right-hand side is 1/5 times sine 5x plus c. Okay. Now another questions are coming. Well, yes, if you would be doing this in a normal environment, then yes, formula sheets are allowed. You can use formula sheets on all classes, on all tests, on the exam. Okay. Yeah, in example 8, we multiply and divide by 1/3. That's correct. That's correct. Well, how many topics we have? It depends how you count. It depends how you count, but if we look at the course contents, then indefinite integral, so I think at least 3 classes, then definite integral. Typically, we have 3 classes for each topic. So indefinite integral, definite integral, double integral, well, introduction to triple integral, differential equations, and series. Yes, I understand that it is a difficult topic. I'm warning you in the beginning that this semester is much more difficult than the first one. Okay, so therefore, what is expected from you that you also need to work at home. By the way, the number of credit points for the course is 4, which implies that you should work, I think, about 20 hours per week on your own. Okay, so that's why the number of classes and classes, instruction classes are not so large, but I expect to work, and we made all efforts to help you. As I mentioned before, there are many solved problems. So if you have difficulties, just go to these solved problems, try to do it yourself, see whether the results that you get the same as the answers. All right, then the next part, we can actually combine the first and the second approach. Okay, the next and the second approach. So this works, for example, for these cases. When you need to integrate, for example, this function, then you need to multiply and divide by 2, right? And then add on the differential sign this constant -7. So in other words, dx can be replaced by this expression here, right? So let's use this approach to solve the remaining problems. So next problem is 10. So the formula to look at in the table is the following. We have used it already. So using this, perhaps you can learn these formulas more. But again, it works if these two expressions are the same, right? In this case, they are not the same. So if we are just missing constants, then perhaps the best thing to do is just to write down what we want, okay? So I would like to have the same expression 2x minus 7 on the differential sign. But if I differentiate this, I get 2, right? So that what I did, I multiplied by 2. I need to divide by 2 to make this formula correct. But then this constant can be added without any further changes. So therefore, the result is 1/2 integral of cosine 2x minus 7 times differential of 2x minus 7. Now we are ready to use this formula, because now we have the same expression here and there, so that the answer is a sine of 2x minus 7. Of course, this constant 1/2 stays in front of the integral. Well, I may not be able to solve all the problems because the next topic is more complicated. Therefore, maybe I will do this example as well. And then we switch to another part. Now, the first thing again, look at the formula. So we will see in a moment that the formula that we need to use, we need to use is the following from the table. So my advice is always rewrite such expression in terms of a power. So 5 plus 2x to the power minus 4, okay, dx. Now, if you compare this expression with this one, we see that now these expressions are different. If they would be the same, then I could have used this formula, but it is not the case. So what do we need to do? We need to multiply and divide by 2 the result. So I'll write down 5 plus 2x here, divided by 2. And you can check that this is correct because the derivative of this term is 2. 2 and 2 are canceled out, so that we'll get the correct formula. Now, since these two expressions are the same, we can use a formula from the table. And the constant 1/2 can be written in front of the integral. So alpha is minus 4, right? So we have 5 plus 2x to the power minus 3 divided by minus 3, because alpha is minus 4, plus c. So the final result is minus 1/6 times 5 plus 2x to the power minus 3. So far so good. Then these are relatively simple exercise, but the more complicated stuff is coming. So let me just switch again back to the notes. So if you understand this property well, then you should not have a problem at all. Of course, you need to work, but conceptually, things will become clear. So what we need to do is to understand this property very well, okay? The question is, how do we compute this integral, for example, in part 5a, okay? So this is a problem. We cannot just say that it is cosine at the moment because it is not clear why, because it looks like we have this extra factor here, and then again, this term. But you can think of the formula that can be useful in this case. And let's assume, okay, what we would have in many cases expression like this, and what will be required to rewrite it like this. So in other words, we kind of insert this product on the differential sign, okay? We can verify the formula. If I differentiate with respect to x and u is the composite function, I need to use the chain rule here. I first differentiate f with respect to u, okay? And then the result should be multiplied by derivative of u prime with respect to x. So sometimes we need to transform this type of expression to more convenient form. Let me illustrate this using the next examples. And this is, as I said before, the most complicated part of this story. So let us do this exercise, okay? Sine of e to the power x times c to the power x dx. Now, if you look at the table of integrals, there is only one integral that contains sine function. And this is how it looks like. Okay. However, we can use this formula if and only if these two expressions are equal. Well, there is nothing we can do about this argument, so we cannot modify it, but we can think of possible ways to transform this expression, right? So another thing which is useful is the following. So that the differential of u is u prime times dx. So I can think of the following, if possible. Can I put some function here, right? So that its derivative will be equal to e to the power x. And with a little bit of analysis, if you open your table of derivatives, the third column in our table of indefinite integrals, the third column contains the table of derivatives. So we will see that actually this is the following. And you can check that this formula is correct. If I differentiate this, you see, we use this formula. So in my case, u is e to the power x. The derivative of e to the power x is e to the power x. So in other words, this means that I can rewrite my integral in more convenient form. So the first term stays the same, but instead of this product, as I mentioned to you, I can just write differential of e to the power x. And in this case, we are done, because now you see that this expression is the same as here. So we can use this formula where the role of u plays c to the power x. Okay. So I agree that this is not a simple thing to understand, but there's only one way to learn mathematics, to do exercises. So that's why maybe I repeat it many times today, but I just want my message to be heard. So if you do and start to work right after this class, then you should do well, I'm sure. But if you do nothing at this point, then it will become very, very difficult for you to follow. So I understand that this is the first day of the semester, but this is how the course is organized. So we start with the most complicated part, right? So from one point of view, it's good because you have more energy after exam session so that you can concentrate more on these studies. Any questions here? All right, we have one. All right. And now let us do some other examples. So this is example number 13. There are some other questions coming. Well, officially, we still had yesterday was the last day of the first semester, right? Do not have such a concept of exam session this semester, and we will not have one also in the spring semester, but we do know that yesterday we finished the first term. Today is the first day of the next term. Well, tutorial session depend on which group you are in. If you are assigned to, if I am your instructor, then tutorial sessions are on Tuesdays. I do not remember exactly when the tutorial session are for the other groups. Just check your schedule, please. Well, I already mentioned that no, I do not record this lecture. I don't record any other lectures, but you do have access, or you will have access to pre-recorded lectures earlier, so you can look at them if you want earlier or after the class. So I thought that we more reserve it for the kind of more or less interactive type of a thing. All right, so what do we do here? if you look at, one thing, of course, is to put the constant in front of the integral sign. But then it is not clear what to do because we have no a single integral which contains logarithm. So there are no such integrals in the table. So which means that we probably can do very little with this term. But then the question is, can we do something with this term? Okay. Can again we rewrite it as a differential of some function here, dx divided by x. In other words, I need to find the function whose derivative is 1 divided by x. So this function is a natural logarithm. You see that in this case, we have to have a table of integrals and table of derivatives. And then if you do this, the problem becomes solvable. Okay. So you can check that this is correct, because if I differentiate logarithm, I get 1 over x, as it should be, right? But now we can use this formula from the table. Okay, with alpha, the role of u plays logarithm, and alpha is equal to 1, right? So that the answer is the logarithm square of x divided by 2.